Ladies and gentlemen, please welcome NVIDIA founder and CEO, Jensen Huang.
Happy New Year! Welcome to CES. I have so much to tell you guys, so I'm going to get going. Usually at CES, I talk to you about self-driving cars and gaming. Today, I'm going to focus completely on gaming. Either you're excited about gaming, or you're excited not to learn about artificial intelligence, robotics, and self-driving cars. But anyways, we have so many announcements in self-driving cars and autonomous vehicles as well. Over the course of the next several days, you're going to hear a lot of news about our next generation of autopilot technology, how we're applying artificial intelligence to the user experience of the car, and how we're using augmented reality to provide feedback to the driver while they're in the car, while the car is driving by itself. We're also announcing a whole bunch of partnerships. I ran down that hall, and I'm breathless. That's it, I'm done. And so we're also announcing a whole bunch of partnerships with map makers all over the world. Between our technology and their technology, we're able to drive in so many different places in the world, whether it's Europe or Japan or China or different places in the United States. So be sure to go see our booth. There's all kinds of amazing technology. Today, I'm going to focus on gaming. The GPU revolutionized modern gaming. There's absolutely no question about it. If you take a look at the last 15 years, which I've shown you a brief history, visual history of computer graphics for video games and some of the most important games that have come out over the course of the last decade and a half, and the technology that made it possible, GPU was at the center of all of that. The fundamental technology that enabled all of this advance was rasterization. Basically taking geometries in a virtual 3D world and translating those geometries, those triangles, into dots on your screen called pixels. That translation process, converting triangles in 3D space to pixels in 2D space, screen space, is called rasterization. Rasterization is incredibly efficient. Computers do it incredibly fast. On top of that, we applied texture mapping that allowed us to put interesting decals on top of three-dimensional objects. If you take a look at Battlefield 1942, this is one of the favorite games of my kids and I. 2002, if you take a look at that video game, basically, there are texture maps on top of 3D geometries. And it was incredibly fun. It was groundbreaking technology at the time, but as you can see right now, it was very chalky. Lighting effects weren't right. There were very few shadows, if any at all, but yet it was incredibly fun. Gears of War took advantage of a technology we invented about 15 years ago called programmable shading. Programmable shaders allowed us to take that pixel that's on your screen and apply a complete large program to it, a really, really flexible program that allowed us to apply all kinds of interesting special effects. Epic, the creators of Fortnite, applied two basic technologies on top of what was available at the time. And one of them was called light mapping, light baking. Basically what they did was they applied the techniques of making video games to the creation of the textures. They did global illumination, beautiful lighting in advance of creating the textures. And then they baked the lighting into the textures. As a result, you could see all kinds of interesting shadows that emerged. They applied also on top of that this thing called pixel shaders that we invented that allowed them to create bumpy and shiny type of effects. Notice how beautiful Gears of War was. Crysis in 2007 was a groundbreaking piece of technology, CryEngine. What they did was they applied really, really fantastic new technologies and took programmable shading to the next level so that we could take these realistic worlds outside, where it's very difficult to bake, Whereas you could bake light inside a room like this and then put that essentially into a texture map, it was very difficult to do that outside in a dynamic world. There's a lot more geometry, light's changing all the time. As a result, shadows are changing dynamically. They use depth of field to take what appears to be in the distance and what appears to be close by, and the close by objects just popped. Screen space ambient occlusion is basically that little dark shadow at the creases of geometries that you see, where where that little tiny piece of geometry lacks the exposure to light. Crisis was a groundbreaking piece of game, and as a result, video games really took a giant step up. Battlefield 3 took it to another level, applied that basic technology, added tessellation, so geometries were really, really rich. We saw no more facets on most of the characters, and when there were explosions, physics were applied, computational physics. Like a supercomputer, physics algorithms were applied so that buildings would crumble, there would be wonderful smokes and particles, and Battlefield 3 was groundbreaking visuals. Battlefield 5 took it yet to another level with a technology called photogrammetry, essentially taking pictures meticulously of the world, and de-lighting it, taking the lights out of it. And what you have left is this beautiful image of the real world, which is then applied as a texture map. That texture map, then applying with all of this great technology and pixel shading, turned into what we see as Battlefield 5. It basically looks like a photograph, and you're in this world interacting with it. It obeys the laws of physics, and it obeys the conservation of energy. So what looks inside this room, inside this world, is physically accurate, what we call physically based rendering. You look at the course of the last 15 years, the technology has advanced tremendously, but yet you stand back and it still looks largely like a cartoon. And the reason for that is because there are three things that are kind of largely missing. There are three things that are largely missing. Reflections aren't right. Shadows aren't right. And refractions are really, really hard to do. These three lighting effects are really hard to do in rasterization, and yet we apply all kinds of amazing tricks to work around them, but it's just really, really hard to simulate the effects of light by starting from a geometry, because you have to start from the light. And that's where ray tracing comes in. About 30 years ago, one of our researchers, Turner Whitted, invented a technology, wrote a paper on iterative ray tracing, and it's taken over 3 decades for the entire industry working together to try to find a way to do it in real time. Tracing a light from your eyes into the world, from your eyes because it's the most clever and the most energy efficient way of doing it, instead of from the light. You trace it from your eyes, only the things that you see. Where it intersects a triangle or an object, it would then follow to the next point of light, whether it's reflected from another object or from a light source. And every single time light touches that geometry, it would affect the color of the pixel, or the lighting of the pixel that comes to your eyes. One ray at a time, we would trace it into the world. And just by doing that, which is basically simulating the laws of physics, the way that light works, and if we capture the materials, we capture the light transport behavior of the medium, we capture the geometry, and if we could do this fast enough, shadows just appear, just like it does in the real world. Lighting just works. Reflection just works. Materials look rich. It just works. No light baking is necessary. No faking is necessary. It just works. That's the beauty of ray tracing. However, the computational requirement is just daunting. And it's taken us 3 decades to get here. And let me show you some of the inventions that we think will be necessary to take it to the next level. And so if you take a look at the top, reflections on ray tracing. RTX on, notice everything is reflected as you would expect. The Rubik's Cube reflecting on the ground, in the mirror, in the sphere. And when we turn, oh, may I do it again? I didn't go fast enough. Did I? How do I do that? Hey, Patrick, help me. I know we're being broadcasted. It's okay. We're among friends. How do I go back? Do I go back? Or do you go back? Okay. This is what happens when you don't rehearse. Okay, so reflections, RTX on, notice everything just works nicely. In the case of rasterization, it uses this thing called a screen space reflection. So it basically takes what is drawn into the screen, into the frame buffer, as the reflection map. And if you can see it on the screen, then it could use it as a reflection. Unfortunately, the things in the back of that Rubik's Cube, you can't see. And therefore, as a result, it can't be used for screen space reflection. And so the back of the Rubik's Cube, which is being reflected into the mirror, because the mirror can't see the back of, using rasterization, can't see the back of the Rubik's Cube, it can't use it for a reflection map. The same thing in that little tiny shelf on that mirror, if I were to turn off RTX off, you would notice that it's broken. Another thing that ray tracing solves is shadows. This right here is called the umbra. Umbra is a Latin word for the eclipse, otherwise known as the shadow. In the case of rasterization, it simulates a shadow by essentially drawing the projection of the shadow on the ground into a geometry. And it does it by using a point light. In the case of area light, some of that light goes to this side, some of that light comes to this side, and as a result, the umbra and the penumbra, the partially occluded parts of the shadow, are not crisp and clear. I wish this would go over again so I can show you. As a result of using ray tracing, we can now have soft shadows. Global illumination. Global illumination is necessary when you don't pre-bake the lights. If you pre-bake the lights, if the world changes on you in the video game, all of a sudden your pre-baked lights don't work. And so notice, this is RTX off. And when the building falls apart, the lighting is just wrong. RTX on, when the building falls apart, it still works. Okay? One of the things that you notice in most video games is the animation is really, really hard to do. And the reason for that is because the world is completely infinite. It's different everywhere you go. And now, because you want to have destructive geometries and transforming geometries, you never know exactly what world you're physically going to be interacting with. Motion capture is nearly impossible for that entire diverse, infinite different degrees of freedom. We use artificial intelligence to train the agent how to navigate. So this is a piece of work from the University of Edinburgh, and the researchers trained an AI how to animate. Facial rendering is one of the ultimate challenges, and the reason for that is because the way the area light affects the face, soft shadows, the occlusions, somehow you see just slightly into the mouth. That's possible because of global illumination. Your skin is semi-translucent, so refraction, the ultimate versions of refraction, called subsurface scattering, all of those effects apply. And then, of course, we want to animate the face. The combination of all of those effects makes it super hard to do with rasterization. That's one of the reasons why most of the video game characters look a little bit chalky and like cartoons. In the future, we could use ray tracing and deep learning and artificial intelligence to make faces that look very human-like. And of course, image processing. Artificial intelligence has the ability to learn what is the right image to synthesize. And maybe as a result of that, we could use lower resolution textures, less amounts of textures, and use artificial intelligence to synthesize the virtual world because, quite frankly, it's natural anyways. And so AI could use it to synthesize higher resolution images. AI could use it to synthesize textures and synthesize all kinds of interesting geometries that we can explore within. AI and ray tracing are two fundamental pieces of technology that we believe will define the next generation of computer graphics. from now on, when Paul says 1.5 minutes, I'm going to believe him. Last time he said 1.5 minutes, it was actually another 5 minutes. And then he said, then all of a sudden, Cheryl was calling my name on the incredible. So we invented a new computer graphics technology to enable the next generation of graphics. We call it RTX, the NVIDIA RTX. In order to enable the next generation of computer graphics, in addition to rasterization and compute shaders, we had to add 2 new ways of computing. One is ray tracing, the ability to trace a ray through a complex world and do it as fast as possible. And then number 2, artificial intelligence. Artificial intelligence for the synthesis of worlds, synthesis of images, synthesis of animation. These 4 key technologies are going to form the foundation of the future of computer graphics. What now the industry is calling, leaders in the industry are now calling hybrid rendering, to combine all of these different types of technologies to generate the final scene and to generate the final AI world, the virtual world. We call it the NVIDIA RTX. It took 10 years for us to reach here. For the last 3 years, we've been working with the industry to create this entire stack, building the foundational technology, integrating it with all of the APIs available in the world, extending it for ray tracing, extending it for AI, and then integrating it into game engines like UE4 and Unity. We then built a brand new GPU to power this new rendering system, the NVIDIA RTX. We call this new GPU Turing. The Turing architecture basically consists of 4 things. The first thing, of course, is the GPU itself, the Turing GPU. The second is a brand new shader architecture. The shader architecture of Pascal has floating point engines on top that are either doing floating point, shaders on top that are doing floating point or integer, but not at the same time. It has L1 cache, shared memory that are separate, and it has a 3 megabyte L2 cache. In the case of Turing, we made it possible for us, we doubled the amount of computational units so that we can do integer or floating point at the same time, and floating point at the same time, and we unified the L1 cache and the register files so that they could be much more fungible. As a result, potentially, depending on applications, adjusted to be twice as big as the Pascal generation. In the case of L2 cache, we doubled its size. We added a brand new engine called Tensor Cores. Tensor Cores has the ability to operate on the deep learning network's fundamental operation of linear algebra A times B plus C, 4x4 linear matrix, linear algebra matrices at the speed of light. It can operate on 4x4 linear algebra matrices, A times B plus C, in one single clock. And it could do it across a whole bunch of modules. And so basically, hundreds of tera floating point operations per second could be processed in one single clock. Okay? We call it the new Tensor Core. And then lastly, in order to do ray tracing, we have a dedicated functionality called the RT core, the ray tracing core, that basically flies through this data structure called the bounding volume hierarchy, which describes the geometric world and deals with all of the intersections of which triangle is hit by the ray and what other rays are spawned from it. That is called the RT core. These 4 characteristics describe the Turing architecture. The performance, the throughput is incredible compared to Pascal. Pascal starts out with the largest version of it, which is now in the Titan XP, and Turing starts out with the largest version of it, which is in the Titan RTX, what some people call T-Rex. These 2 largest chips is what the entire family of Turing and Pascal are derived from. In the case of Pascal, the largest chip is 11.8 billion transistors, almost 500 millimeters squared, has an I/O of 11 gigabits per second using the fastest memory at its time called G5X. In the case of Turing, 18.6 billion transistors, 754 millimeters squared, and 14 gigabit per second, the fastest memory you can use today, called the G6. These two dies is what the entire family is derived from. And if you take a look at these two dies and their computational throughput, you can think of it this way. The compute of Pascal, here we go. The compute shaders of Pascal is 12 teraflops. In the case of Turing, it's 16 plus 16. 16 teraflops, trillion floating point operations per second, and 16 trillion integer operations per second. The shared memory and the register files is 12 megabytes large. In the case of Turing, 25 megabytes. In the case of L2, 3 megabytes to 6 megabytes. Basically, Turing has twice the basic throughput of computational compute horsepower. And if you then add on top of it the 2 new processor cores for tensor processing and ray tracing, you get, in the case of Turing, 130 trillion operations per second and 11 gigaarrays per second. Now, it's possible for us to use Pascal to do both of those things. And the reason for that is because Pascal is a general purpose compute program accelerator. And so it could run tensor operations, just about 1/13 the performance, about 1/10 the performance. In the case of ray tracing, it could also run ray tracing. However, it would have to run it at about 1/10 the performance. You take all of this computational capability and you put it inside this compute framework we call RTX, and on top of the driver called DXR, accelerating driver called DXR, and then integrating it into the Unreal Engine, we can then apply that to do amazing things. This is what I'm going to show you is a demo we've shown you before, except we've made some refinements, if you will. So let's enjoy this. Ladies and gentlemen, everything you just saw, all the lightings, all the shadow, all the animation, everything, all the ray tracing, 100% of it was in real time. This is not a movie. This is next generation graphics. This is what RTX enables. This new form of computer graphics that brings together rasterization for the things that it can do very, very well, ray tracing for the things that it just simply can't do, artificial intelligence that I'm going to talk about later, and, of course, programmable shading that we invented 15 years ago. We could change the time of day, we could change the lighting effects. It just works. All the reflections just work, and the self-reflections work. You could see the reflection on his armor from his arms. And it doesn't matter how you rotate the camera, it doesn't matter what moves around it. The lighting works, the shadow works, and the reason for that is we're simulating light, and it should behave accordingly. Sean, that's fantastic. Everybody, that's great work. Hey guys, let's put a hand together for the engineers and the artists of NVIDIA. Thank you. Thanks, guys. And so that's a demonstration of what's possible in just really a few short months when RTX came to life and what we've been able to do to demonstrate its full potentials. Notice how incredibly physically real it looks. All the materials look so realistic. The lighting looks so realistic. Because our eyes are so acute and we pick out such small details, if the shadows are off, the reflections are off, the lighting's off, we notice right away that something is wrong. This is the next generation of graphics. This is the beginning of next gen. Our partners have been working with us to advance this. And working with Industrial Light and Magic, Epic, who is the creator of Fortnite, the creator of the Unreal Engine, and the engineers at NVIDIA, we were able to bring together all of the pieces of technology to enable this new platform, this next-gen platform powered by RTX. And I won't show the full demo, but I'll show you a short video clip of what that looks like. If you go to our booth, and of course it's all over the web, this particular demo is just so inspiring, and it shows you what's possible with RTX.
What's the story with all the elevators lately? I heard Kylo Ren destroyed the one over in D sector. Who's ever in charge of this place should be transferred to Hoth. What? What? You think she heard us?
The amazing thing, isn't that incredible, guys? Let's put our hands together for all the engineers that worked on it. The reflections, the self-reflections, all of the dynamic reflections, all happening in real time. And so if you look at the shadows, you look at the reflections, they just all look quite normal. The materials look normal, and the reason for that is because it's being simulated properly. Another example that we demonstrated, this one I think we did at SIGGRAPH just in August, was another piece of work that we did with Epic and the folks at Porsche to celebrate their big anniversary. Guys, let's play it.
The speed of light, a universal constant, never diminishing, never ending. "70 years of unrelenting progress.
This is a video. However, in my opinion, it looks better in real time because the resolution's higher. And what's amazing is that the geometry of that car is not a video game car. It's a full geometry of the real car. And the materials are captured physically accurately. And all of the lighting and all the shadows and the global illumination, all done in real time. Just an amazing piece of engineering. Let me show you now. This This is work that's being done by one of the video gamers, Munfest in Eastern Europe, and this is really a fun demo. If you look when we show it to you, you can see that some of the stuff is just really, really amazing, and this is the indication of what next generation gaming is going to look like. Mark, are you going to do this one?
Yep.
Okay, so this is what USSR is was potentially going to turn out to be. Is that right?
That's right.
And so what's really amazing is notice how crisp this is. This can't be a video. This is in real time. Look at this. Everything is in real time. And RTX on, RTX off. Notice the reflections were all broken. And the reason for that is because screen space doesn't allow us to reflect what is behind the object. Notice the soft shadows. The soft shadows result because of an area light. The combination of umbra and penumbra causes the soft shadows to look so exquisite. And that just happens with ray tracing. No shadow maps necessary. There's an area light just underneath this robot, and it's interacting with the light, and it's combined with the light of the head, all being spun in real time. There's a reflection of a curved surface. Reflecting off of a curved surface is super hard to do, really hard to fake, and screen space reflection simply breaks. This is another scene. You're seeing reflection and refraction of that, I guess, what would have been an aquarium. Reflection and refraction. Again, the soft shadows that you notice. Caustics. Looks fantastic. Okay. Wow, I don't know whose lab this is, but it's kind of creepy. Ladies and gentlemen, developers at Munfest. It took 10 years to figure out how to do ray tracing fast enough. And if not because of a groundbreaking piece of work about 7 years ago called deep learning, I don't think we would have been able to realize it in totality. But none of this is possible without the partnership with all of the industry to do so. And so I want to thank Cam and his team at Microsoft, Tim Sweeney and his team at Epic, Natalia's team at Unity, and Tim's team at Frostbite. All of these amazing engineers work together to create what is now the entire stack for this new form of computer graphics that many call hybrid rendering, what we called RTX. One of the pieces of technology essential to making all of this possible is AI. And so now the question is, how is AI applied to the future of computer graphics? Let me give you an example. This is a piece of technology we called DLSS. Basically, with DLSS, what we're trying to do is this. Well, first of all, AI. AI is a machine, a software, that learns from experience. It learns from experience to predict the future, to make a prediction about the future, make a prediction about something. And so what we're doing here is that we're teaching this AI, and we call this AI DLSS. DLSS, it's a very large piece of network, trillions of operations, artificial intelligence network. This piece of software is going to write itself. And it's going to write itself, develop itself, it's going to reconfigure itself, adjust itself, learn by itself, on top of the supercomputer we built called the DGX-2. This DGX-2 has 16 processors in it, 16 GPUs in it, and we have racks and racks of these working away, learning how to predict the perfect frame. It learns from ground truth. Ground truth is 64 times the resolution, 64 samples per pixel. So this picture is beautiful. It learns that that picture should look like this. And wherever it's wrong, we send it back. It's called back propagation. We send it back, and then we give it another try. And it tries and tries and tries and tries again. And it iterates and iterates and iterates again on top of the supercomputer and runs for days on top of the supercomputer, a whole bunch of them. And we're teaching it one frame after another frame after another frame of all different kinds of images. Some of it outside, some of it from this particular style of image, some of it is photographic, some of it's cartoony, all these different types of styles. And it learns from all of this great content what it should look like, what it should look like. And then one day, we give it an image, and it goes through this neural network called DLSS, and ideally what comes out of it is a beautiful image. Ideally what comes out of it is a beautiful image. And the reason why it's a beautiful image is because if I gave you a low-res image, I bet in your mind you could figure out what the high-res image would look like. And the reason for that is because we've learned over years what it should look like, based on the few data points that you were given, what the perfect image should look like. In fact, you could even fill in missing pixels. There could be entire blotches of stuff that's missing, and we could still, because we're intelligent, we could still infer what is likely the right pixels to put there. We call this DLSS. This is the neural network that we created to improve an image. If we were successful in doing this, we could render the original image at a slightly lower resolution, run it through DLSS, and have it put out a larger resolution, and it would look fantastic. Not only would it look fantastic, because it goes through our tensor core processor, it would also do it so fast, it could actually improve the performance. Now, theoretically, suppose we could do AI infinitely fast, and I could render at 1080p and create an image that looks even better at 4K, then what I've essentially done is taken a 10 teraflops GPU, for example, and made it perform like a 30 or 40 teraflops GPU. That's the dream, okay? That's the dream. If we could figure out a way to apply artificial intelligence to predict the perfect pixel because it learned it, then we could render at a lower resolution, and it could create higher resolution, effectively increasing performance and potentially even increasing quality at the same time. Well, we've been playing with this for, you guys have seen us play with this now for several months, and we're making rapid improvement. And just recently, one of the leading developers in the world saw the work, and they were so excited by it, they're going to adopt it for an upcoming title, one of the most anticipated titles, and I can't wait to see it. It's a title called Anthem, and it's a bunch of characters, and they're freelancers, and they jump into these exoskeletons that they call Javelin, and it's an action RPG, and it's just really fantastic looking game. I can't wait to play it. And the folks at BioWare made a trailer for you guys.
Technology has always helped us unleash our creative potential by giving players more immersive experiences than ever before. In Anthem, head out into a chaotic and beautiful world. Fly across wondrous lands in your Javelin exosuits. Confront deadly creatures, formidable foes, and awe-inspiring mysteries. NVIDIA takes us one step further by rendering our game with more precision and higher quality textures. Javelins, creatures, and combat have never looked better. We are happy to announce that we are working with NVIDIA to bring DLSS technology to Anthem. Check out Anthem on PC with Origin Access Premiere on February 15th.
That's amazing, guys. The developers at BioWare just did such an amazing job with Anthem, and I'm looking forward to do our best to make it better. Now I want to show you DLSS in action. There's recently, it was announced that 3D Mark released the world's first ray tracing benchmark. I'm going to play for it. I'm going to play for you here, and we're also going to show you DLSS in action. DLSS in action. Okay, so guys. So on this side is ray tracing on, but using the state-of-the-art in anti-aliasing technology called TAA, temporal anti-aliasing, that we played a huge role in inventing. This is as good as an image quality as you can get today at 1440p. On that side, on your right, is RTX on with ray tracing and DLSS. Both sides are ray traced. Both sides are 1440p. This one uses DLSS, and this one uses state-of-the-art anti-aliasing technology called TAA. I want to bring your attention to two small numbers up on the top. Not only is this image more beautiful, more crisp, it is also running at a higher resolution. Exactly the same GPU. Does that make sense? Are you guys following this? First of all, if you could, a little audience participation here. Who prefers this one? Who prefers this one? Notice how crisp everything is. And the reason for that is because this DLSS network learned from a whole bunch of really high resolution, really beautifully rendered images. And it learned how to reproduce it. It learned how to reproduce it using a supercomputer that we invented called DGX2, running deep learning, this new auto-encoding neural network that we call DLSS. Look at the detailed differences. Remember, both are exactly 1440p. Both are RT on. This one is using TAA. Notice all the subtle details. Temporal anti-aliasing has some static artifacts. In motion, you don't see it, but when it's static, you see a little bit of flickering. If you could just ignore that, DLSS doesn't have that same artifact. But the important thing is, look at the details here. Look at that detail. Look at that detail. Look at the crown moldings on top. Look at the chandelier. It is just incredible from here. Look at the patterns at the bar. This is the power of artificial intelligence. So what have we done? With ray tracing, we added a ton more computing workload. As a result, frame rate drops. We then apply artificial intelligence with this powerful tensor core that's inside Turing that could learn from really high-resolution images and reproduce images that are beautiful, but because the tensor core processor is so fast and so powerful, it could do it so quickly that the frame rate is even higher. And so we now have the ability to not only improve an image, we can potentially even make it go faster. Now let me combine some of this and show it to you in a real game. This next game is called Justice. This game just came out recently in China by NetEase, and this is one of the most popular MMORPG games in China. Calvin, why don't we turn it on?
Okay.
And so here we're looking at justice. Let's talk us through this. Kelvin, you still there?
Yeah, I'm here. Here we see the reflection on the floor and on the vases. RTX off, RTX on.
And notice for all the computer architects in the audience, you recognize what I mean by screen space reflection. Notice the top of the cart is not in the frame. If it's not drawn in the frame, it's not in the screen. If it's not in screen space, then the rasterizer and the programmable shader has no way to reflect from it. And so the information doesn't exist. In the case of ray tracing, the information all exists. Okay, so this particular effect called screen space reflection is used for dynamic reflections, simply doesn't work, and it breaks when the object is not visible in the screen. So this is an example of that. Notice on the vases, none of the objects are visible, and therefore, if RTX was off, all the reflections go away. Okay, Calvin, let's keep going. Look at the ground. Look at all the vases. In this particular case, not only are we reflecting on the water is reflecting light that bounces on top. It's called a caustic underneath that bridge. Lighting underneath that bridge is called a caustic. This is real-time caustics. The first time that I think ray trace caustics has ever been done in the game. Look at under the bridge on the boat. It's just really exquisite and beautiful. Okay. In this next scene, you're going to see fireworks reflected off the ground. And the reason for that is because there's fireworks out in the distance. The fireworks are even outside of the frame. And everything just works by itself. We could zoom into anything with a reflective surface, and it's doing reflections properly. Look at that. It's subtle, it's exquisite. All you have to do is create this ray tracing data structure we call the BVH. You have to trace the rays, which the APIs all provide for, and you have to apply the necessary reflectivity of the materials. And then everything else just works. Calvin, good job. Thank you.
Thank you, Jensen.
Now, the reason why I showed you that is this. This particular game, with RTX off running on the same GPU, Justice in 4K, this video game in 4K, on a 2070 is 50 frames per second, on a 2080 is 60 frames per second, on a 2080 Ti, it's 70 frames per second. With just normal mode, no RTX, no ray tracing. Of course, ray tracing puts an enormous amount of pressure on the processor. There's just a lot more work to do. And so what happens when you ray trace is the performance droops. A little sad. It looks way more beautiful. But the performance is a little lower. And then what we do is we turn on the rest of RTX, which includes DLSS, and it looks like this. Whoop. What do you guys think? You guys want to see that again? Whoop. So next time you guys turn on RTX, I know what's going to happen. You're going to hear this thing in your voice, your brain go, whoop. Just beautiful. Okay? All right, I got to show you one more game. I got to show you one more game. This is, of course, one of the most amazing games ever created, one of the most beautiful games ever created. It's called Battlefield 5, and it's developed by a developer called Frostbite and the division of Electronic Arts. The engineers are just incredible. And I showed you some of the examples of previous works that they've done, and they've done one groundbreaking work after another groundbreaking work. And the latest piece of work that they've done is called Battlefield 5. They were so excited about the potential of ray tracing, and they were one of the early collaboration partners of ours in developing ray tracing into reality, that they put it into Battlefield 5. When we first announced it, people were so excited to see it. When we first rolled it out, the performance was not as good as people expected. And in just a few short weeks, the engineers at DICE improved the performance by 50%. And the audience were just incredibly, the people were so excited about it. Everybody's playing it with RT on. Well, we've been improving it. And here to help me show it to you is Jonas. Jonas, where are you?
I'm right here, Jensen.
Hey, Jonas. Nice to see you again.
Nice to see you
Happy
again.
New Year. Welcome.
Thank you very much.
And Jonas works at DICE. And show us what you're going to show us.
Sure thing. So if you can get it up on the screen. Perfect. So we are visiting the Netherlands again for this demo, the first few days of the Battle of Rotterdam. And one of the methods that we use at DICE to achieve this amount of believability and realism in our game is physically based rendering. So what this means is that if you look at the terrain here, the way that the sun and the light interact with the surface and the materials, you get a physically based look from it. The way the light interacts with it behaves how it would in the real world. And same thing when you look over the water here, you can see the way it reflects. And everything is physically based, which just makes it feel coherent and realistic. But science doesn't get you the whole way when creating a beautiful game, so many of our artists are also taking lots of reference from the real world when creating our assets, particularly this landmark White House of Rotterdam here. Is recreated at almost a 1-to-1 ratio.
Look at that window we're walking by. It looks amazing.
Yes, exactly. So then when
look
you
at that.
look to the right here,
It looks like glass. You could almost reach out and touch it.
yeah, this shows a great example of the combination of ray tracing and our physical-based rendering and the work that we've been doing with NVIDIA. It really comes together here.
Hey, Jonas, look at the reflection of the windows in the buildings, on the buildings.
Yep, exactly.
Yeah, it's just working.
It's super nice. But of course, it's not a beautiful Dutch city without its own beautiful canals. So we can also walk over here. And of course, this is not just any normal canal. It's a ray trace canal. And we see the boats and the barges nicely reflected down there, as you would expect. And everything is looking really nice. But I would like to dive deeper into ray tracing and show you something more. So if we move to another area on the map, then here, to the left in the scene, we have a Churchill crocodile holding, and I have my friend Pavel in there. So if you can say hello to the audience for us, that'd be really nice. Hello there.
Hey, wait. Look, check it out.
That's perfect.
Look at, we can see him nod in the water.
Yeah, exactly. He's reflecting.
Do it again.
Yeah. That's amazing. So yeah, if you could do another favor for me and
now, of course, we would expect that in reality, right? These things that happen in reality, when we're able to reproduce it using computer science, it brings us so much joy.
Yeah, exactly. It's super cool. So yeah, if you can do me a favor and we can start looking at some more ray tracing, if you shoot your fire cannon across the scene here, then with ray tracing on, when looking down into the puddles, even when the flame effects is off screen, we still get the reflective view of the fire as we would expect. But with ray tracing off, when we turn that off, even though the fire is shooting, you can hear it in the background, we don't see it reflected anymore. So then if we turn RTX back on again and we move forward up to the tram cart, then inside the window of the tram cart right here,
oh, look at that.
and again, you can see the flame flying through the scene, moving dynamically. And not only do we reflect the dynamic moving particle effect, we also get a much more accurate representation of the surrounding environment. So, for example, you can see there's a high fidelity reflection of the surrounding city. But with RTX off, then you don't get any of the same fidelity as you would before, even when running the game in high quality. And then we've implemented a special little neat feature in this build for you, so we can slow down the time scale of the VFX. And if we turn RTX back on again, and then we can start shooting the tank's cannon on the sign over there, then we can see the explosion and the debris and the frostbite's destruction is also reflected in the ray trace view.
Wow.
Which, with RTX off, you lose all that detail, and this is just not nearly as exciting as it is with ray tracing on. But of course, we even, with ray tracing on again, we can move to the car, and even complex surfaces like this is not a problem for ray tracing. So when we shoot our tank flame over it again, you can see it on the fender of the car, on the hood, everywhere it's being reflected how you would expect. And a little fun thing is if we move to the back of this car here, and we move around it, then we can in fact see our own soldier reflected in there. Yeah. And that, of course, is together with the flame that's being reflected in the car, and not just the car, also the street windows to the side, in the tram, and everywhere, the whole environment, everything is being ray traced.
That's incredible. Jonas, thank you. Congratulations.
That's great. But I think we have this really, really cool weapon in the game. It's called a V1 rocket, and it's got a pretty big flame. I think it would be interesting to see how that looks when ray traced. So, Pavel, if you can call that in and drop it at the end down there. Let's see how that looks. Right there. And that explosion is being ray traced again in the whole environment, how you would expect.
Oh, you see it in the windows, you see it everywhere. That's really fantastic. Thank you.
Sure thing.
Jonas, thank you. That's incredible work. I think you see now the amount of computer science that's necessary for video games is really quite extraordinary, and it makes sense. And the reason for that is because we're trying to recreate virtual reality. We're trying to suspend you in disbelief. And as the rest of the computer graphics keeps improving, programmable shaders keep improving, photogrammetry improves, geometry tessellation improved, physics is improving, all of these different effects are improving the look of computer graphics, then everything that's broken jumps out at you. Everything that doesn't make sense pops. The things that we really need to go work on are, one, we have to work on shadows, whether it's dynamic shadows or in global illumination, effects of shadow, reflections and refractions. Those three things are so hard to solve. If we can go solve some of those, in addition to everything else that we've done, we could really take computer graphics to the next level. But the thing that is really, really amazing, you saw this entire video game running, this entire demo was running with RTX on at 1440p, But what is amazing is that it was running on a brand new GPU. This brand new GPU, ladies and gentlemen, I would like to introduce it to you. Ladies and gentlemen, the RTX 2060. Incredible. That GPU, that entire demonstration was being run on this GPU here, the RTX 2060, the long-awaited RTX 2060. It is here. So the RTX 2060, 52 teraflops of tensor core processing, 5 gigaarrays per second, 6 gigabyte frame buffer, G6, the fastest memories in the world. Okay? That's what it took to play what you just saw, Battlefield 5, with ray tracing on. Now let's take a look at the performance. What you were looking at, if RTX was off, the frame rate would be about 60 frames per second. A really fantastic experience.